Welcome to our YouTube channel. In this video, we are going to discuss errors, several types of errors that occur during the process of measurement. This measurement can be physical or it can be electrical also. In any type of measurements, you will find this kind of errors. Okay, so watch the video till the end, and at the end of this video, I will ask you some questions from whatever we have learned in this topic. Okay, so let's start. How many types of errors are there? First one is systematic. Systematic error can be predictable. Systematic error can be of positive sign or it can be negative sign. Whenever the measurement is lower than the true value, then we call that there is a negative error. And if the measured value is greater than the true value, then we called that there is a positive error. Okay, so systematic error can be predictable, and if you can understand the nature of the error which will be produced by the measuring device, then you can correct it. Whatever be your measured value, if you know the statistics of the erroneousness of the instrument, I am trying to say that if you have a idea, since this systematic error is predictable, you can easily correct the measured value according to the instrumental error. But you see, there is one another type of error, that is random error. Random error are random variations. There are large factors which contribute to such random error. These errors are a matter of chance, a matter of probability. So you cannot predict random error. Accordingly, you cannot correct random errors also. So if some errors occur due to systematic reason, that can be rectified. But if some error occurs due to random error, due to random effect, that cannot be rectified, and this error will be accounted in measurement. Okay. Now, types of systematic error. There, it can be classified a few types. That instrumental error caused by faulty, inaccurate apparatus. There might be some offset in the measurement, and there might be some offset in the measuring device. Okay, so for that it may show some fixed error. Fixed error. Let us assume that you go to a weighing machine, and the weighing machine represents always every time it represents 2 kg greater than your actual weight. Okay, so if you have the idea, if you already know that okay, this instrument provides a result 2 kg greater than the true value, then you can easily rectify the correction. Then you can easily rectify the measured value and get an idea of the measuring quantity. Okay, so this is an example of instrumental error. Another example is personal error. Personal error that depends upon the observer, who is the operator of the instrument. Depends upon the observer. You know that one type of error is parallax error. Okay. Next is external error. External error which are also predictable. Hmm. External errors can be due to wind, due to temperature, due to humidity. In case of a lot of measurements, for example, temperature measurement, the atmospheric pressure is an important factor. Okay, so if atmospheric pressure is changing, the reading of the temperature will also vary. Okay, so depending upon that, you can say that external error is a systematic error. If you know the relationship between atmospheric pressure and temperature, you can easily derive the mathematical equation, and you can rectify the reading according to the error occurred by the systematic method. Okay, so I am repeating again and again that systematic errors can be rectified, but random errors cannot be rectified. Instrumental error can be rectified. Personal error by the observer, by a good observer, it can be rectified. And if there is a external error, as give you the example of barometric pressure, it can also be rectified. Okay. Next we have random errors. Random errors are subjected to the laws of chance. So depending upon the observations, depending upon the probability, you cannot rectify this kind of errors. So best possible thing you can do, you can take a arithmetic mean. You can take an average of 5 readings or 10 readings, and that average you consider as your measured value. Okay. Now in terms of the measured value, there is a parameter, there is a thing, there is a property that is called uncertainty or variance. This uncertainty of measurement is reflected by the variance. For example, you measure the length of an object 5 times and record the following measurements, as you can see from the slide. And the average, the simple average you get it, and the average is 53.35 centimeter. So basically, you see that uh, the average value is 53.35 centimeter, and the lowest reading you have got, that is 53.32 centimeter, and the highest reading you have got is 53.38 centimeter. So basically at the lower side you have minus 0.03 centimeter, and at the higher side you have plus 0.03 centimeter variance. So basically the total reading should be written as 53.35 plus minus 0.03 centimeter. Another example, there are four readings coming from four different instruments you consider. So what will be the variance? Overall variance will be just simple addition. Okay. The true values will be added. Similarly, the variances will also be added. Errors in multiplication and division. Now if there is a multiplication and division, then what you will do, you will take the maximum value in each case. In this case the maximum value is 13.4, and in this case the maximum value is 23.8. So you get the maximum value of the result. Similarly, you calculate the minimum value here 13.0, here the minimum value is 23.2. Again you calculate the minimum value of the result. Taking the maximum value and the minimum value, the average will be the answer. And as I have told you that, you see, from this average of 3 1 10, this is 9 above and this is 8 below. This is from the average of 3 1 10 centimeter square. This is 9 above and this is 302, that is 8 below. So the overall answer is having a 9 centimeter square variance. Okay, so the variance must be large enough. In the lower side there is 8 centimeter square, and in the higher side there is 9 centimeter square, but you are taking the large one, the maximum one in your answer, that is 9 centimeter square. Okay. Next, accuracy. How we define accuracy? The closeness of measurement to the accepted value for a specific physical quantity. Closeness means closeness between the true value and the measured value. Now accuracy is represented by errors, and there is a mathematical representation of error. One is absolute error, which is the difference between average value of observed values average of observed values minus the true values. If the average of observed values is denoted by xm, it is denoted by xm measured value, and this is denoted by xt. So xm minus xt is your absolute error. Similarly, relative error is given by absolute error upon true value. So absolute error is xm minus xt upon true value, that is xt. Okay, always remember that is the ultimate expression of relative error. So whenever you read any chapter, later on in your syllabus you will study many indicating instruments, many measuring instruments, but in all those cases accuracy will be represented by relative error, and the formula, and that formula of accuracy will be this particular formula, xm minus xt upon xt. Okay, then you have percentage error. The relative error, when it is represented out of 100, it is called as percentage error. So one more thing that you notice, that errors can be negative as well as positive. If the measured value is higher than the true value, then error will be positive, and if the measured value is lower than the true value, then the error will be negative one. Now one more example. You are measuring some acceleration, and while measuring the acceleration, you are getting this 1 2 3 4 5 measured values. Among the 5 measured values, oh, you see the true value is also given. The true value is given 981 centimeter per second square. So among the average value of measured values, average value we are getting 945. The true value that is given 981. So the absolute error will be average value minus true value. You see, this will be negative. Okay, so this one will be negative. This is a negative error, remember that. And the relative error is also negative. Relative error is negative, and similarly percentage error is minus 3.7%. So I am correcting myself, this will be negative error. Next, significant figures. This is one more important concept regarding measurement. Those digits in an observed quantity that are known with certainty are called significant figures. Whenever we are performing any measurement, we have certainty about some of the digits. That always happens due to the uh, resolution of the scale of measurement. Whatever scale I am using for measurement, that scale has some specific resolution, that okay, this scale cannot measure less than 1 millimeter. It cannot measure less than 1 millimeter. So anything less than 1 millimeter I cannot measure significantly. So if there is a measurement less than 1 millimeter, that measurement will be insignificant. So that insignificance is represented by this thing that is called significant figures. Now you see, there are a few examples. Rather, instead of learning some rules, some specific rules, I would suggest you to understand it. I would suggest you to understand with some examples. Here you see, the first example is 67.001. So even after there are two zeros after decimal point, I have successfully measured this one. Okay, so I can say that here the all the digits are significant measurement. So this is 5 significant digit measurement. Okay, next you see, they are 45.0. So clearly you see that point 0, that was irrelevant, but still I have written 45.0. I have written, I could have written 45 only, but I have written 45.0, which means there is a relevance of this 0. So this 0 is successfully measured, and that is why this is significant. So the answer is, this reading 45.0 has three significant digits. If instead of writing 45.0, I would have written 45, then I would have said that it has two significant digits. But you see that I have correctly measured this digit 0. So three significant digits is your answer. Okay. Next you have two significant digits. Since you have, you see, the overall reading, the overall reading is a decimal one. It is less than 1. It is a fraction, right? So basically here we are able to measure only this last two digits successfully. So that is why it is two significant digits. But in case you assume there was a 1 here, then what would have happened? Then we can say that we have measured all the zeros. If 0 is there in between two digits, then that 0 will be counted. But if 0 is at the left hand side or at the rightmost side, then that 0 will not be counted as significant digit. Okay, so I am repeating myself that if there is a 0 between two significant digits, that 0 will be counted as a significant digit. Next, we have one more reading, that is 3000. 3000, you see, uh, only 3 is successfully measured. You assume there is a huge audience, in a hall. Okay, so roughly you are saying that, okay, there are 3000 audience, 3000 viewers have come to watch the show. Okay, so that type of measurement, that is a rough measurement, that is not a accurate measurement, that is a rough measurement. So basically you have only one digit that is significant, that is your 3. Okay, so this is one more important example. You remember that 3000, in this reading only we have one significant digit, that is 3. Okay, so if you are preparing for government job exams, then this kind of questions are very very common. Significant figures, one or two MCQs, they will definitely ask from significant figures. Okay, so let us go to the next portion. MCQs. Accuracy of measurement is determined by, always I have told you that accuracy of measurement is determined by errors. Errors can be classified as absolute error, relative error, and percentage error. But here among these four options, percentage error would be the most accurate. Okay, the percentage errors in the measurement of mass and speed are 2% and 3% respectively. How much will be the maximum error in the estimation of kinetic energy obtained by measuring mass and speed? So if mass is given and speed is given, kinetic energy is given by half mv square. So basically the measurement is directly proportional to the mass, and it is proportional to the square of the speed. So same will occur regarding the errors also. Since the measuring error is proportional to the mass directly, so we will directly take this 2. Okay, and the kinetic energy is proportional to the square of the velocity. Since it is proportional to the square of the velocity, we will take this 3 multiplied by 2. Are you getting my point? It is square of the velocity. So the velocity coefficient is here 2. It will be multiplied by 2. So 2 multiplied by 3, that is your 6. And plus 2, errors are added. Remember that errors are always added. So error in the measurement of mass is 2%, and error in the measurement of speed, that is 3%. So in terms of kinetic energy, in terms of v square, this 3% becomes 6%. So 6% added with 2% will give you a result of 8%. Okay, next, the third question. Error in the measurement of radius of a sphere is 1%. The error in the calculated value of its volume is option A 1%, option B 3%, option C 5%, option D 7%. So basically here the radius is given, and the volume, as you know, the volume of a sphere is given by 4/3 pi r cube. If the radius is given by r, and the volume will be given by 4/3 pi r cube. So I hope that you can calculate the answer, and please give the answer in the comment section. I am not going to tell you the answer. You tell the answer of this MCQ in the comment section. Okay, I will let you know the true answer. Okay, so thank you. Thanks for listening to the lecture. We'll meet again in our next video. Thank you.